From this lecture onwards, we will start the new chapter with the name Series Parameters of a Transmission Line. But before going on to that topic, we will study some little bit things about the types of conductors being used in transmission lines. First of all, when electricity was started for transmission, copper was thought of as the best choice as a conductor because of its very high conductivity compared to other metals. But soon, the high cost was a detrimental factor in planning of new transmission lines. So the world shifted over to aluminum conductors. But the problem with aluminum is it has a lesser tensile strength, and we also gain an advantage because of its lower conductivity also. As we all know that aluminum has lower conductivity as compared to the copper. Because of that, for the same current carrying capacity, we need a higher cross section area for the aluminum conductor. Because of that, we get an advantage. What is the benefit in that? We will study in later chapters that there is some effect called corona at very high voltages. What happens that at very high voltages, there is high potential gradient in the periphery of the conductor, and because of that, the air may get break down. The dielectric strength of air may be surpassed by this voltage gradient occurring in the periphery of the conductor, and there occurs a breakdown of the insulating medium, that is air. This causes loss also. This corona also causes interference in other communication lines if they are going besides the transmission line. But as we increase the cross section area of the conductor, or rather I would say the dia of the conductor, the effect of corona is reduced. The potential gradient over the periphery of the conductor gets reduced. So in a way, when we use aluminum conductor in place of copper conductor for very high voltage lines, rather I would say extra high voltage lines, the corona effect gets reduced, and it is an additional benefit in using aluminum conductors. So first of all, when the world shifted to aluminum conductors, the conductors were totally made of aluminum. Means there was nothing inside them with the central strength of central strand of steel or something else. All the strands were made of aluminum, and it was termed as all aluminum conductor, means AAC. Next came AAC, means all aluminum alloy conductor. Instead of aluminum, we started using some alloy of aluminum. It had higher tensile strength. But again, we caught up with the various problems in those conductors, and a new conductor came called ACSR. Means aluminum conductor steel reinforced. What was new in that we used the central core of the conductor, it was made of steel instead of aluminum. Since we know that steel has higher tensile strength as compared to aluminum, this conductor ACSR had higher tensile strength, so the problem of sag was reduced. It has lesser sag. But there is a disadvantage also. We cannot use it beyond 75 degrees Celsius for continuous operating temperature. So the loadability of the line is reduced in high temperature areas. In ACSR, what is there? We have central strand, let us say made of steel like this. Let us say the central core is made of say 7 strands. 1, 2, 3, 4, 5, 6, 7. Let us say this is the central core of the conductor. It is made of steel. Now the aluminum strands will come over it. The aluminum strands can or cannot have the diameter or radius same as the central steel strands. It depends on the design of the conductor. they may or may not have the same radius as compared to the central core. Let us say now comes the layer of aluminum strands. Although the drawing is not very clear, the circles are not round enough, but we can see that over a central strand we have aluminum strands. And let us say if in a conductor we have 21 aluminum strands and 7 central strand, we can write it like this 21Al7 or simply 21/7, meanings that the central core is made of 7 steel strands and the conducting part is made of 21 aluminum strands. As we know that steel has higher resistivity as compared to aluminum, so the most part of the current will flow from the aluminum part only. So the conductivity of this conductor is comparable to its predecessors. Next came, because of this limitation of working up to 75 degrees Celsius only, we designed some new conductor called ACSS, that is aluminum conductor steel supported. It could work beyond 150 degrees Celsius. What was the change in it? We used highly annealed aluminum conductor in it, and the steel part was there for providing tensile strength. In ACSR, some part of tensile strength was being provided by aluminum strands also, but in this ACSS, the tensile strength part is given totally by the steel strands, not the aluminum ones. And since it is highly annealed, the operating temperature is also improved. Further, the thermal coefficient of expansion of steel is lesser, and in all, ACSR and ACSS both have lower thermal coefficient of expansion. That is, the expansion or contraction with temperature, that is the change in length of this conductor with temperature, is lower as compared to their earlier versions. Now research is already being done. It is a continuous process since we are trying to achieve higher voltage in transmission. So we try to get new type of conductors. The new one is like there is one conductor GTZACR, means gap type ZT aluminum conductor. What is that? There is a conducting part made of aluminum alloy, that is usually aluminum zirconium, and there is a steel core inside it. After steel core, there is a heat resistant grease over it, and over that we have trapezoidal shapes of aluminum zirconium strands over it, making it GTZACR, means gap type GT aluminum conductor. That is, there is a gap which is filled by heat resistant grease. Now research is also being done in carbon composite fibers. We have a conductor called ACFR, aluminum conductor fiber reinforced. Now there is one more topic in ACSR, that if the radius of central steel core strands and the aluminum strands is same, we can find out the total dia of the conductor if we know the dia of one strand and the number of layers we know. Here there are 1, 2, 3 layers. So let us say if dia of one strand is D, then total dia of conductor will be 2n-1 D, where n is the number of layers and D is dia of one strand, and capital D will be the total dia of the conductor. And if we want to know what will be the number of strands, if we know the number of layers, it will be 3x square minus x plus 1. If I know the number of layers, then I can find the number of strands using this formula. But this formula is applicable only when the radius of the central steel core strands and the aluminum strands is same. The nomenclature of conductor is also a little bit different in industry. Like we call it by some names like ostrich conductor, zebra conductor. Similarly, one type of conductor in GTZACR is Matthew conductor. So when we go into the industry, we will see that various type of conductor with various diameters and number of strands, they are given a different name for their identification, and the names are usually in the name of some animal, bird, or sometimes some other thing. Now in the next part we will study about the resistance. Our next topic is resistance of conductors. But before going on to that topic, there was one little point left in previous topic. Why do we need to make stranded conductors? If I make a totally solid conductor, say like this, what will happen? It will be very difficult for me to place this conductor because of its high weight and reduced flexibility. Due to lesser flexibility, it will be very difficult for me to string it over the poles. So that's why I make this conductor as stranded. If I take a section of this, the totally solid conductor will be fully solid. Okay, but in stranded conductors, if I take a section of stranded conductor, let us say it is a standard conductor. If I take a section of this conductor, what will I see? I will see various strands. Like this. I will see various strands. Stranding provides us flexibility. And one more thing, these layers, let us say this is the central part is the first layer. Now this is the second layer and this is the third layer. These layers are spiraled in opposite directions. Let us say if it is spiraled in clockwise, then it will be spiral anti-clockwise. Okay, it is spiraling means we push it like this, bend it like we try to bend these wires cyclically or anti-clockwise, so that the strands, the layers do not get unwind. They do not get unwind while laying or something else. That's why we spiral these in opposite directions. That is, spiraling is done in opposite directions. Okay, and stranding is done for higher flexibility. These are the added advantage of stranding the conductors in place of using a totally solid conductor. Now coming on to the resistance part. It is a well-known formula that R is equal to rho L by A. What is R here? Resistivity. Let us say R is in ohms, length is in meter, and this is in meter square. L will be the length in meter. A is the area in meter square, and R is in ohms. What will be the unit of resistivity? Simply ohm meter. This formula gives us the DC resistance, that is the resistance of the conductor when we force a direct current through it, DC current through it. That is, the current does not vary with some frequency. But as we will see that whenever we try to pass an alternating current through a conductor, the resistance is little bit different. The resistance, it is RDC, RAC is greater than RDC. First one, due to skin effect. We will study this skin effect a little after studying this RDC and other things. Further, as we have seen that we have stranded conductors. The R equivalent is also increases. The R equivalent increases due to stranding. Why? As we will see that the central strand will have the same length as that of conductor, but the strands, they will have spiraling like this. So there will be an increase in length. L dash will be greater than L, that is length of outer strands will be larger than length of conductor. This stranding causes R to increase by 2 to 3%. Similarly, skin effect causes R to increase by 2 to 4%. The figures are approximate ones. It is not a hard and fast rule that the increase in resistance will be only 2 to 3%, but usually it is there. Now we will study the change in resistance with temperature. As we all know that resistance of a conductor is dependent upon temperature by this formula. Where R is the resistance at temperature T, R naught is resistance at temperature 0 degree Celsius, and alpha naught is coefficient, thermal coefficient of resistance. We are assuming that this delta T is change in temperature, that is T2 minus T1. We are assuming that this delta T is small, so the value of alpha naught is constant over that range T2 minus T1. Then we can give the resistance at temperature T by this formula, R naught 1 plus alpha naught delta T. So let us say I have R2 at some temperature 2, it will be T2. Similarly, R1 at some temperature T1 will be R naught 1 plus alpha naught T1. Let us say this is equation 1, this is equation 2. I will divide these two equations. What I will have, R2 by R1 is equal to 1 plus alpha naught T2 1 plus alpha naught T1. I will take alpha naught common out of this. What I will have, 1 by alpha naught plus T2 1 by alpha naught plus T1. This, since alpha naught is a constant for a given conductor, this 1 by alpha naught is also a constant. Let us say it is K. K plus T2, K plus T1 is equal to R2 by R1. Now in next slide, we will try to plot a graph between R and T. As we have seen in the last slide, that resistance is temperature dependent given by this formula. R at temperature T is equal to R at temperature 0, 1 plus alpha naught, where alpha naught is the coefficient of thermal coefficient of resistance and T is the temperature. And we also derived that R2 by R1 is equal to K plus T2 by K plus T1, where K is equal to 1 by alpha naught. Now, if I plot this equation on a graph with temperature at y-axis and resistance at x-axis, we will see that at a higher temperature, the resistance will be higher. At a lower temperature, the resistance will be higher. And also, the graph is a linear one. The graph of resistance and temperature is a linear graph. So, the graph is a simple line. If I extrapolate this line to, let us say, if I get somewhere this resistance is 0 resistance point, and I put this value 0 here, 0 is equal to R naught 1 plus alpha naught T. T will be minus 1 by alpha naught is equal to minus K. So the temperature here will be minus 1 by alpha naught or minus K. Usually the manufacturer provide us with K, this value, and by using those tables we can determine the resistance at different temperatures, even if I don't know other factors. Just the condition is that I should know the resistance at a reference temperature, let us say at some 20 degrees Celsius or 0 degrees Celsius, and I am given this K. I can find R2 at any temperature using this formula. I will be given K, and I will be given temperature T2 also, and I will be given temperature T1 or the reference temperature also, and the resistance at that reference temperature. Using this equation, I can find R2. And in that way, I can find the resistance at various temperature. And similarly, this is helpful in dealing with calculating the resistance or the current carrying capacity of a conductor and its change with temperature. Whenever we try to find change in resistance with temperature, as we know that transmission lines are laid in very long length. They can go in deserts or some cold places, so there will be a lot of temperature difference in a single transmission line. So these equations help us to find the resistance variation with temperature.